So we will start with the machine. Okay, so this is the machine. If you want to visualize, there is some machine, and what this machine does is you can give it a number and this machine will give you back a number. You give it a number and the machine will take some time and it will give you back a number. We just encountered this machine, we do not know what it is doing, so we will just experiment with it. We'll just give it some numbers and see what it does. So I'm going to give it some numbers. Let's say I give this 2356. So basically, how do I give it? I write it in a strip of paper and I give it to this hand, and then it will just dance a bit, and then it will give me a strip of paper from this hand, and that will have another number written in it. So after all this computation, this machine will give me back 356. I gave it 2. After some time, I got an empty paper back. I gave it 3324. After some time, I got 424242. And I gave it 1234. It gave me again an empty tape. So it looks very weird, right? There's no logic in what this thing is doing. And then let's say some people spend some time trying to analyze how the internal wiring of this machine is and try to come up with some logic behind the input-output function that this machine is computing. And they figured that this machine is just simply following just 2 rules. There are just 2 governing rules for this guy. The first rule is that if you see rule 1, any number which is of the form 2x. 2x does not mean that it's an even number. It just means that the first digit of the number is 2. 2 followed by a sequence of digits. If you give it a number of the form 2x, the output will be just x. It will just remove the first 2. Okay, the first digit is 2. So whatever is remaining in the sequence, that is what it's going to give it back. And the second rule is that if you give it a number of the form 3x, it starts with the digit 3, the output will be y to y if x gives you y. Let's take some time to understand that. Okay, if the number starts with a 2, it will just ignore the 2 and output whatever was remaining. If the number starts with a 3, let's try to understand what this x was going to output. If x was given as the input, what would this machine output? You put that output there, put a 2, then repeat that output once again. Okay, that is what this machine is going to give if the input starts with a 3. If the input starts with any other digit, it's going to give you nothing. That is what happened here. If the input starts with a 2, it's going to give you what is remaining after the 2. Here it is starting with just a 2. So after that 2, there is nothing. So you again got a blank tape. Okay. And the first one you can see 2356. So after the 2, what you get is this 356. And if you see this 3324, we have to first find out what would you get for 3 to 4. What do you get for 3 to 4? That's again some digit that's going to start with a 3. So we have to first find out what you would get for 2, 4. 2, 4 would just give you 4. So the output for 3 to 4 would be 4, 2 and then a 4. So 4 to 4. Okay. So the output for 3 to 4 is 4 to 4. So the output for 3 to 4 would be 4 to 4. Then a middle 2, again a 4 to 4. You understand how this machine works? So this machine, people figured out that this particular machine is working just with these 2 rules. There is no other rule. Okay. So some such machine is given to us. So this is the machine, it is following these 2 rules. Now we will just try to analyze this machine. We will just ask some questions about this machine or the functions computed by this machine. The first question is, there is a number such that when you give this number as the input, the output you are going to get is exactly the same number. Okay? What is that number? That is the question. Yeah. Find it. Do you want me to display the rules again? The question is, you want to give the number as the input and you want the same number to be obtained back as the output. Show me. Just take 2 minutes to think about it. Okay. So if you have to analyze, if you have to analyze, we will see that if the number is starting with a digit other than 3 or 2, it's going to give you a blank tape, so it's not going to give you the same number. If it is going to start with a 2, the output will be at least length, it will be length 1 less. So it cannot be starting with 2 either. So it has to start with a 3, for sure. So you have to have a number that starts with a 3, okay, and the output has to again start with a 3 because the input and the output should be the same. So if it is 3 and something, our rule was that this part gave you some output y, and what we want to put is that y, 2 and then a y, right? Yeah, so this part should give me something that starts with a 3. If I want to make sure that this part outputs something that starts with a 3, so let's just try. Maybe it can start with some 2 and then you put a 3 so that it starts with a 3. Right, and that just works. So for example, this y can be 3 and then you will get 3 to 3 here. So that would work. So this is this number which will give you back itself, okay? The next question. Now I want to find the n such that when you give n as the input, you want 3 followed by that number as the output. Not 3 times the number. The first, so it's that number plus 1 more digit on the left, and that extra digit should be a 3. So this will not work for this one, right? Because it's just keeping all, n is giving back you only n. You want to add a 3 in the beginning. How can you get that? Just show me. Yeah. Yeah. So if you give it 3, 2, 3, 3, what would be the output? So 2, 3, 3 would give you 3, 3, right? And then you want to put a 2 and then again put 3, 3. So what you will get is 3, 3, 2, 3, 3. This is exactly this number and a 3 before it. So it is possible that you can have a number that gives you back the same number. You can get a bigger number, a longer number as output. All these kind of things are possible. Sometimes you can also get a shorter number as output. Of course, you start with a 2. This can happen. So there is this machine. Now out of curiosity, some people then just decided to change this machine slightly. Okay, how do you change it? So, if you give it some input, it's going to give you a paper strip and some output there, right? You want to give that output back to itself as an input again. So, it's just going to make this thing a feedback. So, you give it the first input, whatever number you want. It will produce an output, then that will be fed back to it again after a minute. Okay, so it keeps on going on like a loop in this one. So this is my new machine. So this is the feedback machine. But the underlying principle is the previous machine. I changed it like this. Now you just instantiate it with one input and then it will run on this loop. Okay, until it stops. So with this machine, my question is there a number that makes this machine perpetual? The machine should not stop after that. 3 to 3, right? So on 3 to 3, it will keep on getting this 3 to 3, 3 to 3, and so on. Another number? 3 to 3 to 3 to 3 to 3. You can even write this simpler examples that we wrote before. 3 to 3, 3. This was giving you 3, 3 to 3, 3. That would also make it just keep growing. Yes. And what about this number? 3, 2 to 3. That will give you 2, 3, 2, 2, 3. And that in one more step will again give you 3, 2, 2, 3. And then it's going on a cycle. So there are many numbers which will make this machine go on forever. Okay, and definitely there are some other numbers on which this machine after a few rounds, it's going to die. Okay. So now this machine is there with us. Now we are going to classify numbers. A number is called immortal if that number makes this machine go on forever. And a number is called mortal if the machine eventually dies out. Okay? You understood? This is the feedback machine. And in this feedback machine, if the machine goes on forever, then that number is immortal. Otherwise, the number is mortal. Now, we are interested in understanding, given some number, whether that number is mortal or immortal. In fact, so here for some numbers, we could just work out and see that, they were mortal or they were immortal. More than that, we want to now come up with design a machine. So you can give it a number n. It will either say you it is mortal, or it will tell you that it is immortal. So this box has to be filled in with a machine. Okay, so in other words, since it was all functions from numbers to numbers, let us say that if it is mortal, it is going to tell you, it is going to give you 0 as the number as the output, and if it is immortal, it is going to give you 1 as the output. Okay, so you are giving it any number, the output of this new machine is going to be just 0 or 1. 0 means that it is mortal, 1 means that it's immortal. Do you have a machine? Not yet. But yes, there is some similarity. It's about termination, right? So, just I'll give you 2 minutes to think about. Yeah, so the halting problem is about your machine. I'll tell you about halting problem in a while. So this is just that machine that we had before, the feedback machine. I want to just know whether a number will make that feedback machine run forever, or that feedback machine terminate after some time. This is what I want to know. What would be a naive way of answering that question? What we did also previously, when we had some numbers to see whether they were mortal or immortal, what we did was we just tried giving that thing as the input to the feedback machine. We looked at what were the intermediate outputs after every step, and if we saw some kind of looping pattern, we said that okay, it's going to be immortal. If loop need not be exactly the same number, maybe a bigger number, but we kind of see that it's growing, or we see that it's kind of something is decreasing and it is kind of going to terminate. But the thing is that when you give something like this, we may not be always able to come up with some such pattern which will enable us to identify that it's going to go on forever or it's going to stop. I'm not sure about that. You can put a 2, and then any number that makes it immortal, if you put a 2 before, what would happen? Take any immortal number, prefix it with a 2. Other than 3 or 2 in the beginning. Yeah. So let's just come back to our previous idea of we are just trying to run this thing on this machine for some time, and if it terminates, if it eventually comes and ends and there is nothing else given out, then we know that it is mortal. But if it is immortal, we do not know. We do not have a proof yet. Maybe after some time it is still not going down, but it may go down, then it may go to a bigger number, maybe it may go down to a smaller number, we do not know. In such a case, it is convenient if we have a extra thing, something like, let's say, hypothetical number h. Such that the following holds. N is mortal if and only if Hn is immortal. This is for all n. A number is mortal if and only if you put this h before it, then that number is immortal. If we can come up with such a hypothetical number h, then we can solve this problem of identifying whether a number is mortal or immortal. How can we do that? Exactly. We make a copy of that perpetual machine once again, not unperpetual, that feedback machine once again. And to one of the copies, we will give n, and to the other copy, we will give hn. Since one of them necessarily have to be mortal, one of those machines will terminate. And if it was the hn machine that terminated, then we know that the number was immortal. If it was the original machine that terminated, we know that the number is mortal anyway. So at least one of them would terminate. So if we could invent such a hypothetical number h, then we do not have then we can solve this problem of checking whether a number is mortal or not. Now our next task is to show that there is no such hypothetical number h. Yeah. The definition is that so h is a good hypothetical number for me if for every n this thing is true. So to show that such an h does not exist, what we have to say is that no matter what h you propose, there is a number which will violate this. Yeah, it can be of arbitrary length. You can make it of whatever digits you want. No, just 3. Just 3 or 3 followed by something? Just 3. The output is nothing, right? Because nothing is going to give you output, nothing. Maybe you can think that it is 2. I don't know. Yeah, maybe 2. Can you just try to come up with something like that is what I want. So can you get whatever n you give, can you get some number n such that in one step you will get hn? The number is immortal, then any suffix of that number is immortal. Maybe we need a proof, but Somebody is there in the waiting room. Okay. So, I think your ideas are correct. All we need to come up with is that if there is such an edge, you come up with a number n such that this if n is mortal and h of n is also mortal, or n is immortal and h of n is also immortal, then you are good. So what I am just saying is that suppose there is such a number h, then your objective is to come up with a number n such that eventually after some time, maybe not in one step, but in after several steps, this n itself will produce hn. And then you are in a contradiction for this statement, right? Because if n was mortal, then this hn is now also mortal. No, maybe, I mean, yeah, I'm only saying that this claim, such a number h cannot exist. That's all I'm trying to show. Yes. Suppose we can come up with a number such that this thing holds, then I'm saying that we can just have a machine which will do this mortal/immortal business for us, if there was something like that. And what we are claiming is that something like that cannot exist. Yeah. Yeah, we will see this. So just to say that there is no such h, what we have to show is that suppose there is an h, then I will come up with a number n such that this number eventually will give you hn. So which means that either both of them are mortal or both of them are immortal, because it's the same computation which is going to, along in the feedback loop, in between it's going to show you this one. So now the question is, no matter what h is, can you come up with a number n, of course which will depend on h, such that this number after some time will give you hn. Yeah. H has to come somewhere, right? Because it has to depend on the h. Yeah, you were there, yes. Yeah. If h was 3, we could do that, but for arbitrary h, can I generalize it? You can, you're almost there. Just see which bit you need to change to h. 3 to 3h is going to start with a 3. We have to make it start with an h, right? No, you have to find that n such that eventually you want it to start with hn. Yeah. So I hear this 3 2, so I'll put 3 2. What do I put next? You want it to start with h, so I put h. Yeah. So, but do you want it to start with a 3? So, just start a 3 after this one, maybe. If you have 3 to H3, what does it give you? H3 to H3. This is what we started with. So it is exactly that 3 to 3, 3. You just replace that in that middle 3 with that whatever long sequence of digits you have. You can put that thing and you would get this. So it's just a... no, we just showed that such a hypothetical number h cannot exist. It can neither be mortal nor immortal, right? Because of this. It's like a paradoxical thing. So we are deriving a paradox here. So that is what I'm saying. If there was such an h, then we will get into this paradox. That's the problem. It's with respect to this. So that's it. Playing with the machines. We will stop here. But just to now introduce you to some of the concepts that we show here. So here we started with some very specific machines that that 3 something goes to that y2y and 2 something goes to something. So we only had 2 rules, but it can be even a more structured things with more specific rules. Let's say something which is written in a C program or a Java program or something. It can be any code. And the kind of things that we asked, like, is there a number which will make it go on forever? Is there a number on which you're going to get the same output? These are exactly the kind of questions that you would be asking in program analysis. Okay? These are the kind of questions that you are asking in program analysis. Instead of this machine that we saw here, what you would have there is a code. Maybe something with 30,000 lines, maybe something with 100 lines. Some code, you do not need to know what is inside. Maybe sometimes we look inside and we kind of say that these are the rules they were following. But the final questions that you want to ask is, if I give some input to this program, is there an input to this program which will make this program go on forever? These are the kind of questions that we want to ask. And then essentially when I was asking, can you design a machine which will do something like this? I'm asking, can you write a program which will take another program and say whether it will terminate on some input or on some input. So then when I'm asking this question about programs, this is the halting problem. Yeah. So all of these interesting questions that we ask about programs, it is known that there is no program which can do any of these things. Is there a number on which it is going to terminate? Is there a number on which it is never going to terminate? Or given 2 programs, is there a number on which they are going to give different outputs? Or this is in other words asking, given 2 programs, on every input are they going to give you the same output? Are they equivalent? So all these problems, we know that there is no program which can check this. Okay, so this is the big negative result that we have in terms of computability. This is called Rice's theorem. Any non-trivial property about so there is no program to determine any non-trivial property about programs. Okay, in roughly speaking. This is called Yeah, I did not show it. I'm just saying that, that usually we will see in the end of a 1 semester course on computability. I'm just making the claim here. And we also need to define what these programs are, even for this thing to make sense. But maybe many of you are familiar with usual programming languages. Any programming language with 2 integer variables, then this is the case. This is called Rice's theorem. So we were starting with this simple machines. So Rice's theorem is like, you don't specify for with this particular program can you do something. You do not know what that program is. The question is, can you come up with a meta program which will take two programs and check whether they are actually the same? And then it's the impossibility result. It just says that something like that cannot exist. And the proof, I'm not going into that proof again here, but the proof will also often use something like this self-reference, similar to the feedback that we were seeing there, that is n going to hn, that kind of thing. So it cannot be at the same time both. If it was going to give a yes answer, you will be forcing it to give a no answer, and if you are forcing it to give a no answer, it will be forcing it to give a yes answer. So this kind of paradoxical situation will come. But I'm not going into that. This is how that proof also goes. So it's really logical reasoning going on behind all of these things. By the way, this puzzle about numbers is taken from a book by Raymond Smullyan called The Lady or the Tiger, and some logical puzzles. So it's a puzzle. Now I will show you some simpler kind of machines which will also compute functions from numbers to numbers, much simpler than the machines that we saw before, for which checking whether two things are the same, I mean, we can come up with a program to do that. We can decide it. We can determine it. Okay? A simple class of machines or whatever, simple class of functions from numbers to numbers. But it's much simpler. But there are also interesting things that you can, functions that you can program using this new programming paradigm. And this new programming paradigm is graphs. All of you are comfortable with graphs? Okay. So this is the graph that I will draw. So the graph has vertices and edges. I'm not looking at simple graphs, so there may be multiple edges between a pair of vertices. Okay, and I mark some vertices. So this is called an initial mark. This is an initial or a source mark, and this is a target mark. Okay, so I have a graph and I identify some subset of vertices called initial and some subset target. And this graph, I defined this graph to compute a function from natural numbers to natural numbers in the following way. The number n will be mapped to the number of paths of length n from source to target. For every number n, it's going to give you another number. What is that number? It's the count of the number of paths of length n. Length n paths or length n walks in the graph, however you want to see it, from some of these initial vertices to some of the target vertices. So in this particular graph that we have here, what is the image of number 0? How many paths can you see? Huh? These are target with this dangling outgoing edges. You can still move. There are no paths, or it could have, for it to have any path of length 0 from initial to target, the initial should also have been target. That is possible. If that was the case, then that would have been 1. In this particular graph, that is not the case. So 0 would get mapped to 0. What about 1? How many paths do you have of length 1 from initial to final? 0. What about length 2? Which are those two paths? So either I can take this one and then come here, or I can take this one and come here. So I can take 2 paths. Actually, the 2 paths are to reach here, and from here to come to a final state, there is only one way, which is just to take this one, right? So there are two paths of length 2, right? So 2 will get mapped to 2. What about 3? Both of these are target. There can be multiple initial, multiple targets, not problem. Yeah. So just by going with this top path, you can go to the top path, then stay here once again, and then come down. That's the path of length 4. You can go here, stay here once, then come down and then go there. That's another path of length 4. We are looking at path of length 4 or 3? Length 3. Okay, then I remove one more thing. Okay, so I come here, I take this, I come down here. So that's one path of length 3. I come here, I come down here, I go there. That is another path of length 3. So already by starting with this one, I have 2 paths of length 3. Instead of this edge, I could have taken this edge as well. I will again get 2 paths of length 3. So total I will have 4 paths of length 3. Right? And so on. So this graph, you think of it as a program. Okay, or a machine or whatever. You give it a number n. The output that it gives is the number of different paths that it has of that length. Which? Okay. And this one, you mean? Yeah. This one is going up. This is the one that's going down. Okay. So if I give you a number, no, not a number. If I give you a function, now your exercise is, you have to come up with a graph that will realize this function, that implements this function. Okay. Yeah, just programming with graph. Yeah. Finite automata do not do this. It's not computing functions from numbers to numbers, but it's similar to that. What is the difference between a finite state automata and a graph? Yeah, but it's only a number here for me as an input. I don't have words or anything. I can what the adjacency matrix? Yes. Yeah. Yeah. Very nice observation. Yeah. Okay, so let's do the programming with graph exercises now. The first function that you have to program is the constant function. Okay, any n will map to 1. Just draw a graph and show me, which will realize this function. No matter what n is, show me the graph. Yeah, so you have to put the mark for the, yeah. Everybody knows how to get this one? Yeah, a single self loop would do this thing, okay? Very good. So this is the initial, this is also the final, and I do this thing. No matter what is the length, it's always going to be one path of that length from initial to that thing. What if I want F3? Every number I want to get 3. What did you say? Make one vertex? Let's draw that. I will draw some suggestions here, okay? Let us see. This was one suggestion. This, you yourself said that it is not going to work, but tell me why. And the other suggestion, so this was one, and the other suggestion was this. There were 3 suggestions. Any more suggestions? We will analyze them. Yeah, I'm not saying that any of them is correct or any of them is wrong. I'm just collecting your suggestions. We will analyze them. Any more suggestions to go there? A graph need not be connected. So, what is this graph computing? 3 to the n. It's not computing 3, but it is computing 3 to the n. Okay, it's an exponential function that it is computing, because for every position, if you want, it could have taken any of the 3 edges. So it's going to give you 3 to the n. Okay, so this is going to give you 3 to the n. What is this one doing? What does 0 map to map? What does 0 map to? 0 maps to 0. What does 1 map to? What does any other number map to? Okay, so how does 0 map to 3? Yeah. So this function is not, this graph is not correct for the function that we wanted. Okay, so this is not the constant function 3, because it is not giving me 3 for 0. The last one, no. No, n is not mapping to 0 here, because it's the initial and final. So I have a path of length 0, which is just that state. I don't take any edge, but even without taking any edge, I'm already in the initial and final. Yeah, but then the initial and final has to be the same. Only then you can stay there like that. This is for? This is same as that. No, you are putting something back here. Yeah. So what does this graph compute? This compute the constant 3. In fact, you can notice that, so this computed 1, this computed 1, this also computed 1, and you are just adding them. That is therefore free. Yeah. Any constant you mean? Yes. Okay, let's look at a slightly more interesting function. want to now program, get a graph for this function. Give me a graph, means graph has certain number of vertices and edges. That's it. That would work for any n. Okay. So the input is, yeah, the graph has to be finite, yes.
First is final, is initial and final. This is final. Like loop like double stop.
I'm not sure. I think it computes more. I think it computes more than n. There are more. Yeah. I think it's a bigger function that return is doing.
There's a two parts, right? But it has to go back to because
Just think about some bigger number and see how many paths are there. That works. Yeah, just remove the one. Remove the one. There is a part that is doing a one. So make sure that it is not counting the one. Can you just change it? Yeah. We have time until 4:45, right? You have a proof that it is not possible. Okay, what is the proof? Mm, mm, mm. Is this only what? Yeah, there will be a cycle in the graph. Yes. No, why? We had the constant one and that also had a cycle. I did not make it exponential. Why should there be two ways to go to that cycle? Your intuition is right. If there are two ways of going into that cycle, then it is going to count some exponential. That is true. But why should there be two ways of going into the cycle? What is 3? The constant function 3. Okay, yeah. Yeah, that would work. You have an infinite graph, but infinite graphs are not okay. I want finite graph. So there is some graphs that I saw that some of you wrote, which is like this. What is this graph doing? This one is computing n. Do you see why it is computing n? Why? Why is it computing n? Yeah, but just the intuition. Exactly. So there has to be one point when it jumps from here to here for it to be accepting, and there are exactly n choices for that one point. So it's exactly n choose 1. Yeah, so n choose 1 is n and you get n. How about n square? The next function is n square. Yeah, can you just draw and show me? N square. Yeah, but how do I get n square? Yeah, but that is not n square. Okay. Yeah. Yeah, how do you get n choose 2? Now just show me how do you get n choose 2. And the next question is n cube. Huh? 3 to the n. No. So this is not a finite graph. The degree is not bounded, right? Eh, No, so that's what. So n is going to be part of your input. You do not know. N can be arbitrarily big. So we have to give one graph which will work for every n. You understood this one, right? It works for every n. So something like this. So here you have to just choose one point to jump from here to there. Now to get quadratic, you need to choose 2 points to go from initial to final. And that is how it's going to help you. Yeah. So for n choose 2, you can have this thing, right? 3 states. Yeah. So you have to pick 2 points the first point you will jump to the middle one, the second point you will jump to the third one, right? So this automaton is computing n choose 2, which is n into n minus 1 by 2. So in order to get n square, what you need is this is n square. Okay, you can see that this path here, this is an n choose 2. And this path is also an n choose 2. And this diagonal is an n. How will you get n cube? N choose 3, yeah. How do I draw a cube? Yeah, the same thing only, I'm just drawing it. There are self loops everywhere. And then we will also draw the diagonals. Okay, by the way, without drawing the diagonals, if this is the initial and this is the final, right, the diametrically opposite things, one is initial, one is final. What is this computing? It's going to be, it's paths of length 3, right? All of them are paths of length 3. How many different paths do you have? You will have 6 paths. Do you see that you have 6 paths from this vertex to the diametrically opposite vertex? So it's like 6 times n choose 3. So because it's n into n minus 1, n minus 2 divided by 6. And now you have to add, now we have to add 6 times nc2, which I am going to add like this. 1, 2, 3, 4, 5, and 6. Okay, let me use a different color. Yeah, so those, the n choose 2, 6 n choose 2, I am adding like this. So in any of the faces, if you take a diagonal, you are getting an n choose 2. And then you have to add the n, which is the final diagonal. So it's really a cube that is going to compute the cube. After that, I don't know how to draw it pictorially, but basically it's the same thing. Now, okay, so your intuition is right, we can compute polynomials. And we can compute many more things. We can compute exponentials, some 3 power n we saw, many more things. Okay? Now, what is interesting is that I started by saying that we can check, given 2 such functions, like given 2 such graphs, we can check whether these 2 graphs are actually computing the same function. Okay? So I'll just give the high level intuition, I don't give the proof. The idea is that given just a function, we want to know whether this function is just going to be the constant 0. In other words, is there at least one n for which the value is going to be non-zero? Well, here it looks very simple because we are just in the naturals and we are only counting. If there is a path, then it seems like there should be something. But generally, when you draw these graphs, here we were just enumerating everything, but we can just put a weight on every edge. Okay, so in general, when you draw these graphs, you can draw things like this and you can say this is -2 and this is like +5. So this +5 would correspond to say that there were 5 paths there. -2, of course, will multiply whatever thing that's the -2. So you can do all those things. Even you can put initial weights like 3, here the final weight is -2 and all that. All those things you can write. So in fact, you can put any weights, any integer weights, be it positive or negative, integer weights you can put. And the question is the function computed by such a graph with both positive and negative weights, is it going to be the constant 0 or not? This is the question. So essentially I want to find out if there is at least one n for which the value is going to be non-zero. In other words, for every n, the value is going to be the constant 0. To do this, high level idea, what we want to see is, we want to look at what is the current number of paths which have reached this state. What is the current number of paths which have reached here? What is the current number of paths which have reached here? This I can represent it as a vector of dimension 3 here because there were 3 states, or otherwise of the number of states, many things. So I will have some n1, n2 up to nk if there were k states. It's a tuple of k numbers kind of describing at any point after reading, say, let's of for length n or for the input n, how many paths have currently reached this state, how many paths have currently reached that state, etc. Now if you want to increment this by one more, if the function was for n plus 1, assuming that you have these numbers n1 to nk for n, when you want to increment it by 1, you want to just see how this thing gets distributed to the other states, how this thing gets distributed to the other states, etc. Which is really, who was telling here, the adjacency matrix. It's exactly multiplying this whole thing, this vector with the adjacency matrix, that will give you the new vector. Right? So just multiplying with the adjacency matrix will give you the new vector. Okay, now let us look at all these vectors that you would get here. So since there are only k states, the number of linearly independent vectors that you can have is at most k, that's dimension k. Okay, so you will get a basis for this vector space, at most k with k vectors. For each of those basis vectors, you just check whether from there, if you were just stopping it at that point, just multiplying from each state with the final weights, is it going to be a non-zero value? If at least one of them is going to give you a non-zero value, you know it's going to be a non-zero value. Otherwise, every basis is going to give you 0. So any linear combination of the basis will also give you 0. So you can check for whether the value is actually equal to 0 or not, given a function. It's constant 0, or is there a number n for which the value is going to be non-zero? Now that we know how to do this, now given two functions f and g with two different graphs, okay, what we will get is, we will find this new big graph which is just a disjoint union of these two things, okay, by putting a minus here. It's f minus g. That is going to give you f minus g, and you just check whether this f minus g is 0. And how would this f minus g graph look like? In the adjacency matrix, here you will have the adjacency matrix for f, here you will have the adjacency matrix for g, and here all you will have 0, 0. Okay, and what will be your initial matrix? So this is the part for f, this is the part for g. Here you have to just put minus g. You have to just put a minus sign in addition, because you want to get f minus. And the final things are exactly the same. So you just multiply this. So in this new thing, you just check whether it's actually going to give you 0. And if it is the case, then f and g were indeed computing the same function. So you can check whether they are actually equal or not. But these things, of course, it can compute using graphs. You can compute any polynomial, any some exponential functions, Fibonacci number, for example, some recurrence relation functions. And there are things that you cannot compute, like, some 2 power n, 3 power n you can compute, but 3 power n square you cannot compute. 3 to the 3 to the n you cannot compute. So there are things that you cannot do with this also. Anyway, so this is just a model of computation. And in theory of computation, you will be studying different models of computation. What are the things that you can compute using them? What are the things that you cannot compute using them? And then ways to formally prove that something can be done or something cannot be done. You can even prove that, mathematically that something like this cannot be done using this kind of models. So computability theory is all about that. What can be computed, what cannot be computed. So with these graphs, many things can be computed. Even analyzing them is also fine. But with arbitrary programs, analyzing them or checking whether they are two different programs are equivalent, that is not possible. Yeah, okay. So I stop here. Any questions or any interaction? Yes. No, so this is mathematical. Yeah. So this also kind of corresponds to the, so there are many natural cases where you would need negative weights and you require that to be modeled, and it need not be always just natural numbers with multiplication and addition. It can be actually any semi-ring and anything. So so with the addition, something is that, for everything there is a distance or time spent and you want to increase it, or some cost involved with it, and maybe some actions you do, maybe you are getting some cash. Okay, and some things you have to pay something to do that. So that positive and negative would make sense there, but in an additive way. So here we are in the multiplicative way. I have not thought about it, but there are definitely situations where these are also needed. Multiple edges? No, I don't know. I do not think so. Yeah. Yes. No, not all of them will be linearly independent, but we will not have more than k linearly independent vectors, right? Because they are all lying inside R power k. Yeah, that's all. So we can just start enumerating from beginning. The first vector that you reach, which is by not, like non-zero, what is the vector that you get? Then on 1, then on 2. So you keep on finding, discovering new vectors as long as you are, like you have discovered something, you multiply with the matrix, you will get one more vector. Okay, and you have kind of collected all the linearly independent vectors. When you get the next one, no, the moment you get something which is not linearly independent, you can stop. Because now onwards, that thing what you got now, it's already a linear combination of this. Now when you multiply with the next one, it's going to, because it's a linear combination, that you can distribute across those sums. Okay, so you can stop there. The moment you hit the first thing that is not linearly dependent, you will stop. Okay, and you will not need to do it for more than k steps, for sure. It may actually end even before k, because you may have k states, but the number of linearly independent, so maybe k is 100, but maybe you have only like 5 independent vectors. This is also possible.